Hello everyone, my name is Blaha Gregory Correia dos Santos Goussain from São Paulo State University, UNESP. It is a pleasure to present this research titled Durability of Aerodrome Horizontal Markings, a literature-based framework linking AI, lifecycle optimization, and sustainability. In this presentation, I will walk you through the factors that influence the durability of airport pavement markings, the regulatory landscape, technological developments, and how artificial intelligence and lifecycle thinking can enhance safety and sustainability in aerodrome operations. Over the next 12 minutes, I will guide you through the main findings of this literature-based study and the framework we developed from them. Aerodrome horizontal markings play an essential role in aviation safety. They provide visual guidance to pilots and ground personnel during landing, taxiing, and gate operations. However, these markings degrade over time due to climate, traffic load, material properties, and maintenance practices. As degradation advances, visibility decreases, increasing operational risk. Despite their importance, many airports still rely on reactive repainting practices rather than predictive maintenance or life cycle optimization. This creates safety vulnerabilities, unnecessary costs, and sustainability challenges. Therefore, a systematic and multidisciplinary framework is needed, one that integrates engineering knowledge, materials science, life cycle thinking, and digital predictive tools. The central research question is, what determines the durability of aerodrome horizontal markings, and how does this durability affect operational safety? From this, 4 key objectives emerge. 1. Identify the environmental, operational, and material factors affecting performance. 2. Evaluate marking technologies, coding chemistry, and application methods. 3. Examine maintenance practices from both cost and sustainability perspectives. 4. Develop a literature-based framework that links durability with life cycle optimization and digital predictive tools. Together, these objectives aim to support more informed and proactive decision-making in airport infrastructure management. Horizontal markings are not merely visual aids, they are safety-critical infrastructure. They define runway edges, touchdown zones, center lines, taxiway routes, holding positions, and apron pathways. Markings must comply with standards issued by ICAO, FAA, and in Brazil by RBAC 154 and NBR 8169/10855. Retroreflectivity is especially important in night operations, wet pavement, and low visibility conditions. Runway markings are white, while taxiway and apron markings are yellow, following international conventions. Any loss of visibility or clarity can compromise situational awareness and increase risk for both pilots and ground crews. Therefore, durability is directly connected to operational safety. When comparing regulations, we see important differences. ICAO and FAA provide well-defined performance thresholds, particularly regarding retroreflectivity and bead quality. High-quality glass beads are mandatory to ensure visibility under various lighting and weather conditions. In contrast, Brazil's RBAC 154 has less standardized retroreflectivity criteria, and national norms such as NBR 8169 and NBR 10855 define composition and minimum visibility requirements, but offer limited durability guidance. This creates a regulatory gap. Markings applied under Brazilian standards often exhibit lower durability and clarity, requiring more frequent repainting and exposing operations to risk. Durability results from the interaction of 4 main groups of factors: climate, including rain, ultraviolet radiation, and temperature cycles that accelerate degradation. Traffic, especially abrasion from tires, rubber deposits, and landing impacts. Materials such as paint chemistry, bead morphology, and application technique. Maintenance, where reactive practices often lead to premature deterioration and higher life cycle cost. Understanding how these factors interact is essential to improving marking performance across airports. UV exposure causes yellowing and fading, reducing daytime visibility. Rain and surface wetness reduce retroreflectivity because the water layer changes the refractive behavior of glass beads. Thermal cycles cause microcracking, brittleness, and binder degradation. Studies consistently show that UV absorbers, additives, and high-performance binders extend service life. In hot climates, these modifications may significantly reduce overall deterioration rates. Traffic intensity is one of the strongest predictors of marking degradation. Touchdown zones, high-speed taxiway entries, tight taxiway curves, and apron areas experience the highest mechanical abrasion. Accumulated rubber deposits reduce visibility and require aggressive cleaning, which itself contributes to wear. Research shows a strong correlation between the number of operations per day and the frequency of repainting cycles. Marking performance is strongly linked to material quality. Glass beads play a central role. Their shape, sphericity, refractive index, and adhesion determine retroreflectivity. Thermoplastic coatings offer superior durability compared to acrylic paints. Recent innovations include 3D printed bead dosing systems, which ensure uniform distribution, and high refractive index beads, which significantly enhance visibility. Advanced UV absorbers and cross-linked polymers further extend service life. These developments show that material innovation is a powerful lever to improve overall marking performance. Maintenance strategy has a major impact on durability. Preventive maintenance, such as structured inspections using indices like APCI, enables proactive interventions and optimized repainting schedules. This reduces life cycle cost and minimizes operational disruptions. In contrast, reactive maintenance, waiting for markings to degrade before repainting, leads to higher costs and lower safety outcomes, and is generally less sustainable. Airports that adopt preventive routines tend to achieve better long-term visibility and fewer repainting cycles. Based on the literature review, we developed a conceptual framework composed of inputs, climate conditions, traffic intensity, material quality, maintenance practices, analytical tools, artificial intelligence models, especially neural networks, probabilistic degradation models, advanced materials, 3D printing technologies, outputs, longer marking durability, higher operational safety, lower life cycle cost, improved environmental sustainability. This framework helps integrate multidisciplinary insights into airport pavement marking strategies. Artificial intelligence has shown strong potential to improve marking management. Neural networks can predict retroreflectivity degradation more accurately than regression models, especially when climate and traffic data are available. Probabilistic models quantify uncertainty and support repainting cycle optimization. AI enables airports to shift from reactive repainting to data-driven planning, reducing risk and lowering cost. This is aligned with the growing trend of digital transformation in airport infrastructure management. From the analysis, 4 key insights emerge. 1. Durability increases significantly when high-performance paints and high-quality glass beads are used. 2. Reinforcing materials in traffic hotspots prevents rapid degradation. 3. Preventive maintenance consistently outperforms reactive repainting in durability and cost. 4. AI-supported predictive planning reduces uncertainty and enhances life cycle optimization. There is a clear trade-off. Higher upfront material cost leads to lower lifecycle cost, stronger safety performance, and sustainability gains. Airports can greatly benefit from adopting lifecycle thinking instead of short-term cost decisions. High-quality markings reduce operational disruptions, repainting frequency, and environmental impact caused by solvents, waste, and repeated application cycles. In Brazil, regulatory updates may be needed to better align national standards with ICAO and FAA benchmarks, ensuring more consistent durability and safety. Based on the review, we propose the following recommendations. Adopt abrasion-resistant paints and high-quality glass beads. Implement preventive maintenance programs with structured visual indices. Use AI-based predictive models for repainting optimization. Conduct life cycle cost-benefit analyses before selecting materials. Align national standards with international retroreflectivity requirements. These recommendations support safer and more sustainable airport operations. This study is based entirely on the published literature. There were no field measurements or retroreflectivity data collected directly from airports. Variation in methodologies across studies limits quantitative generalization. However, the literature provides consistent patterns that support the development of the proposed framework. Future research should investigate real-world retroreflectivity monitoring in multiple climates, long-term life cycle cost studies across airport categories, testing of nanomaterial-based and smart paint coatings, integration of AI models with actual airport operational databases. These directions can strengthen the scientific foundation for marking durability and maintenance planning. In conclusion, the durability of aerodrome horizontal markings depends on the interplay between climate, traffic, material technology, and maintenance strategy. Digital tools and innovative coatings significantly enhance performance and visibility. Preventive, data-driven strategies improve safety, efficiency, and sustainability. Ultimately, life cycle optimization is essential for modern aerodrome operations. Thank you very much for your attention. If you have any questions or would like to discuss this topic further, I would be happy to talk. You may contact me at blaha.goussain@unesp.br.